Okay, so chapter 43 is called Energy from the Nucleus. And we talked about this already a little bit from the nuclear reactions or the decays that we just had, but we'll do it a little more rigorously here. So the nuclear reactions, there's really sort of three types of nuclear reactions. There are the decays that we just did in chapter 42. It's really not a reaction when a gamma comes out, because all you're doing is having a nucleus that essentially goes from an excited state to a less excited state. It's really a nuclear reaction in an alpha or a beta, because you're actually taking one nucleus and you're turning it into a different atomic species after, right? There's actually something that's changed about the species of the nucleus. But in chapter 43, we talk about real deal nuclear reactions, which are fission reactions and fusion reactions. So fission is, as it sounds like, you take one large nucleus and you divide it into two sort of largest nuclei. This is not a decay. You have a big nuclei and you turn it into another really big nuclei and an alpha particle or a beta particle. Those things are not big. And alpha is at least a nucleus, but beta is not even a nucleus. With a fission, you're really making two things. One's bigger than the other, but they're both fairly large nuclei even afterwards. Fusion is when you do the opposite, and you start with two small nuclei and you fuse them into one larger nuclei. The energy that comes out is going to come you're going to get energy out of these reactions as long as your products have a larger binding energy per nucleon than the reactants. In other words, as long as if you go from this side, on this side, if you take these and you bind these together, then you're moving up and your reactants have larger binding energy per nucleon than others. So as long as you're moving up along here, you take small nuclei and you bind them into larger nuclei, you fuse them, then you can get it. Or if you go on this end and you take these things and you split them so that they become this, so you can also split large nuclei. So because again, you're moving up the axis here. But when you get to things like here, you can't do anything with these because there's nothing that you can do. Anything you did, if you moved this way, it'd have less binding energy. If you went this way, it'd have less binding energy. And so these are the most tightly bound, are at this peak, and you really can't do anything there. It's sort of nickel and iron. All of these are the things where you can't bind things together. You can't get any energy out of a nuclear reaction. No energy out of nuclear reactions, fission or fusion, or at this peak. And notice that iron is there at this sort of peak region, and that really is important in stellar astrophysics and black hole formation. So fusion, again, energy comes out in a fusion reaction because you fuse small nuclei and you can fuse them basically until nickel. Fission, energy comes out by splitting large nuclei again until you get to nickel. It's too small. Let's talk about fission specifically. So fission, basically you need a reaction, and at least you need a driver or a catalyst. It's unlikely to just happen on its own, unlike a decay. You need to have something that was actually going to make this happen. It doesn't have to be anything crazy. Normally in these fission reactors, and this is what we have in nuclear reactors here on the Earth, nuclear reactors, and bombs, with the one exception, not an H-bomb. Not that that's made anymore. But most nuclear bombs are fission reactions, where we have things like plutonium or uranium or something really big, and we have a fission that goes on. And certainly all nuclear reactors that are commercial are fission. There are attempts to make fusion reactors, but none of those are working at any kind of commercial level power production at this point. So what we do is we bombard the nucleus with a neutron. The neutrons don't have any charge, right? And so it isn't hard to get a neutron to go into this nucleus. It's not going to be repelled like if I tried to throw a proton into there. The proton would just come right back at me. But if I throw a neutron at this nucleus, that can cause it to become unstable and start to fission. And so here's a reaction of uranium-235. I add a neutron to it, and it splits into xenon and selenium. Is that what that is? SN. We'll just say it's SN. And again, we can see here, these are both big nuclei. It's not an alpha particle and something else that's much, much bigger. We have two fairly sized nuclei. And what's interesting is that what also comes out of this reaction are two more neutrons. Those two neutrons are now free to go and find two more uranium-235 nuclei. And so we can cause those to fission, and we can cause a chain reaction. This only works if you actually have an enrichment, if you have a lot of uranium-235. Now, uranium-235 is not the most common isotope of uranium, and so you have to enrich your uranium. In other words, you have to sit there and try to deliberately make uranium which has a higher percentage of 235 in it than the natural 238, which is usually what's there, the most common isotope. And so, and we see situations where countries or organizations are trying to enrich uranium, then we start to wonder, what are you going to do with that uranium? If you want a chain reaction, if you just want to make nuclear power plant level chain reactions, you really only need an enrichment of around 20%. But if you want a nuclear weapon, then you need to have an enrichment which is much greater, something like 85%. And so you can tell what the purpose of this enriched uranium is going to be, depending on what level of enrichment they're going for. And again, it's because you throw one neutron in there and you're immediately going to get two more out, and so you can drive it. You basically can start these reactions by having just neutrons in there. In a nuclear power plant, what you would be able to do is also put in material. If you wanted to slow down your reaction, you could put in material which absorbs those neutrons and slows down the chain reaction. I don't want to get into all that. But anyway, so again, our energy that's going to be released is from our equation that we've had last chapter and previously, where we take the mass that we start with, we subtract the mass that we end with, and then we multiply that times c squared. And so we can actually do that for, this is actually a slightly different reaction that we can get out of uranium-235. We throw a neutron at it. So let's go ahead and do this. So the mass that we have initially is our uranium and our neutron. So if we add those two up, and then I'll go ahead. So then the mass we have finally is the rubidium and the cesium. So, sorry, the mass at the end is the rubidium, the cesium, and then two neutrons, right? And the mass initially is the uranium and one neutron. And so my initial mass is this, my final mass is that. So Q is my initial mass minus my final mass squared. So I'm sorry, C squared. So I've got my initial mass in there. 235, 85852. I have 0.19406 U times C squared. And every time I'm doing this, every time I have U times C squared, I'm just multiplying this number by 931,494,013, because this is essentially how many MeV per C squared there are in one U. So I can just multiply that by that number, 013. And so I get that I got 180.766 MeV of energy that's coming out of this reaction. Now that's for one reaction, for one uranium-235 reaction. If I had a whole mole of 235, then for a whole mole, I would basically say Avogadro's number times 180.766 MeV. Now, an Avogadro's number, for those of you who are not chemistry majors, is 6.022 times 10 to the 23. So this is the energy that's coming out of a mole. So let's multiply that. 6.022 to the 23. This is 886 times 10 to the 26 millions of electron volts. So 1.0886 times 10. If I write this instead of millions of electrons, I actually write it, and ME is 10 to the 6, so this is actually 32 electron volts. And even if I convert this to joules, where I basically am going to multiply that times 1.602 times 10 to the negative 19 to get it into joules, I end up with 1.74 times 10 to the 7 joules per mole. That's the amount of energy that's coming out here. Writing that in kilojoules per mole, which is more typical. Right, I need to write that, take away 4 kilojoules per mole. Give me a second for a second. Let me check something for a second. Yeah, sorry, I knew I was off there by something. This is actually 10 to the 13 joules per mole, or 1.74 times 10 to the 10 kilojoules per mole. This is like the Gibbs free energy. This is the energy that's coming out. The Gibbs free energy for this reaction per mole is this much. You're getting 1.74 times 10 to the 10 kilojoules of energy out for 1 mole of uranium. How does this compare to a chemical reaction? So this is the burning of carbon, right? This is your typical carbon burning. You take carbon and oxygen and you combine it and you get CO2. The Gibbs free energy, which for our non-chemistry majors, Gibbs free energy is essentially the energy that comes out of a reaction, is 394.39 kilojoules per mole. 394. For a whole mole of carbon, that's how much energy you'd get out when you combined it with oxygen. Comparing this, so writing that out in joules per mole, it's about 3.9 times 10 to the 5 joules per mole compared to what I just had, which was 1.74 times 10 to the 13. I'm getting 44 million times more energy out of my nuclear reaction per mole than I am out of my chemical reaction. And this fact that you get so much more energy out of a nuclear reaction is just a sign of how much stronger the nuclear force is than the electrostatic force. Maybe I'll just leave this in here and leave it in my notes and not talk so much about it, but even in a chemical reaction, even in a gravitational reaction, where you have things get closer together and you get energy out from the gravitational force, mass is what's being lost. You have less mass after than you do before if you're getting energy out of a situation. It's just that energy, that amount of mass is too small to measure. So if all the energy that's released in this reaction is coming from a change in the potential energy, the internal energy of the system, and not from, say, the entropy and the volume parts of the Gibbs free energy, if that's all coming, so if this energy per mole is coming from a change in the mass of the two, of the products and the reactants, the carbon and the oxygen separate and then the carbon dioxide afterwards, the amount of mass difference here would be this. If I sit there and basically divide that by c² and figure out how much mass I have to lose per mole, I'd only be losing something at 10 to the negative 12 kilograms per mole. And that's just too small to measure. I can't measure something that's that small when I basically am starting with, so if I had 12 grams of carbon and 32 grams of oxygen for a mole of both of them, so I have 44 total grams in my reactants. I'm only missing this 4.4 times 10 to the negative 12 kilograms. Or if I write that in grams, I'm only missing 4.4 nanograms. I'd have to be able to measure my masses of my samples here to the 9th decimal place, and I just can't measure that. But in a nuclear reaction, we really are losing something much, much smaller, a noticeable amount. So if we're losing 1.94 times 10 to the negative 4 kilograms per mole, what that means, we're missing 0.194 grams per mole, and I can measure a loss of that small. In fact, we are measuring masses that are those losses. All right, yeah. That's not something I'm going to test you on, but just recognition that you do have less mass afterwards, no matter what reaction you're talking about. It's just usually that smaller amount of mass is not something that you would ever be able to measure. Leaving you again with fission. So fission again is going to leave me with two product nuclei that are usually also radioactive, but they're not useful in any kind of nuclear power or nuclear weapon sort of situation. And so I'm going to have to go put them somewhere. This is the great, one of the big objections to nuclear power is that the waste that we're left with afterwards has to be put somewhere. It is a messy thing. They are toxic still to humans. They are dangerous across the board, and they could be used in dangerous ways if they aren't protected, as well as being put away somewhere so they don't hurt anybody. And so it's been, I think, a general concern about nuclear power is what do we do with the waste afterwards? And also, maintaining the nuclear power plants in a safe way. They aren't meant to last forever. And so what do you do with those power plants afterwards, and do you maintain them? Where's the money coming to maintain them while they're running? But that said, nuclear power does not produce any greenhouse gases, and so in that sense it is clean. All right, I'm going to do fission in the next video. Fusion in the next video.